Greetings. Good days to you, global citizens. My name is Dr. Avans Lee. I write to fellow designers, entrepreneurs, investors, and visionaries who are exploring industrial applications of plasma technology and seeking new pathways to transform materials processing at a global scale. Over the past years, I have had the opportunity to design and operate a high-power plasma smelting system based on a 700 kilowatts, 22,500 V arc plasma configuration. This system was successfully deployed in Pyeongtaek, Republic of Korea, where platinum group metal-bearing ores were directly smelted using plasma energy. Unlike conventional batch melting processes, the system was engineered for continuous smelting operation, enabling a designed processing capacity of up to 10 tons per day. The furnace was operated in campaigns of approximately 20 continuous days per month, demonstrating the capability to process roughly 200 tons of feed material within a single operational period and produce concentration-enriched PGM ingots. While large-scale commercial production still requires further investment and expansion, the technical feasibility has already been validated. The project progressed beyond laboratory experimentation into pilot industrial operation, including plant construction, system optimization, demonstration campaigns, and the successful production and sale of approximately 100 kilograms of PGM ingots. This experience confirmed not only the scientific validity of plasma smelting, but also its practical industrial potential. Building upon these results, my current focus is the design of a fully robotic, mobile, and modular plasma smelting system. The objective is to create scalable metallurgical platforms that can be deployed rapidly, operate autonomously, and dramatically reduce infrastructure constraints traditionally associated with high-temperature refining facilities. With the collaboration and support of entrepreneurs and investors around the world, this technology has the potential to fundamentally change how critical metals are produced. Without relying on chemical reagents and avoiding the environmental burdens of conventional hydrometallurgical processes, plasma smelting may enable production rates that are at least 10 times, and potentially up to 100 times, greater within the same operational timeframe for platinum group metals and rare earth elements. To help a broader audience understand the scientific and industrial foundations of this approach, I intend to introduce and explain the technology based on the principles presented in the Handbook of Thermal Plasma, making its possibilities accessible to engineers, investors, and curious minds alike. The material may appear highly technical at times. Nevertheless, I hope readers will revisit it more than once and find the process both rewarding and intellectually enjoyable as understanding deepens. If this vision resonates with you, I warmly invite your interest and communication. Contact fabrics.of.universes@gmail.com. Mailto fabrics.of.universes@gmail.com. Thank you for your time and curiosity. Figure 27 summarizes man-made thermal plasma sources by nominal power rating in kilowatts and plasma velocity in meter per second. Most sources operate near atmospheric pressure or under soft vacuum conditions. Plasma sources designed for ballistic and aerospace reentry testing are a notable exception. The map in Figure 27 is useful for selecting a source family when both power delivery and jet transport matter. The same source families often trade jet velocity against achievable power and operating stability. This overview sets the frame for practical devices used in cutting, spraying, metallurgy, testing, and analysis. Hot cathode plasma torches are widely used for plasma cutting, welding, and plasma spraying of coatings and near-net-shaped parts. In these torches, an electric arc heats a partially ionized gas, and resistive dissipation converts electrical input into thermal plasma. Electrical conductivity requires a sufficiently high degree of ionization, so gas temperature must be high. For many plasma-forming gases at atmospheric pressure, required temperatures are around 8,000 Kelvin and above. Figure 28 shows a typical torch where the arc is struck between a central cathode and a cylindrical annular anode nozzle. Plasma gas enters near the cathode base, is heated by the arc, and exits the nozzle as a high-temperature, high-velocity jet. In plasma spraying torch designs, electrons are supplied by thermionic emission from the hot cathode. Tungsten doped with 1% to 2% by weight of low work function additives such as thorium dioxide, lanthanum oxide, or lanthanum hexaboride is commonly used for the cathode. These additives reduce cathode operating temperature and extend cathode life. The anode is usually a water-cooled copper channel and can be lined with tungsten or tungsten copper sleeves. Arc column behavior depends on energy dissipation per unit length, which is set by arc current, plasma gas flow rate, gas composition, and arc channel diameter. Nozzle and gas injection designs are used to keep the anode arc route moving and to stabilize the emerging jet. The plasma jet leaving a hot cathode torch is typically highly turbulent and exhibits continuous motion. Figure 29 presents results from three-dimensional simulation of the arc inside a plasma torch and photographs of the emanating plasma jet. The simulation highlights how arc attachment and flow recirculation can vary in time and space. The photographs reinforce that the external jet structure fluctuates and is not a steady laminar plume. This turbulence influences heat transfer to particles and substrates during plasma processing. Torch design therefore uses gas injection geometry and nozzle shaping to control stability and useful jet characteristics. Arc route motion on the anode can be enhanced by magnetic rotation. Figure 30 shows a torch concept where a field coil surrounds the anode region. An axial magnetic field interacts with a radially oriented arc current near the anode attachment point. This interaction produces a tangential electromagnetic force J cross B that drives arc route rotation. Rotation is most effective when the electromagnetic force direction aligns with the aerodynamic vortex direction. Strong vortex motion, with or without magnetic enhancement, has been used to reduce electrode erosion in multiple torch designs. Hot cathode arc plasmas are a mature technology for metal cutting and welding. TIG welding uses a transferred arc where a non-consumable tungsten cathode is inside the torch and the workpiece acts as the external anode. Inert shielding gas such as or helium is directed along the cathode to prevent contamination from ambient air. MIG welding also uses a transferred arc mode, but the electrode is a consumable wire fed continuously through the torch. In MIG welding, inert gas is delivered into the weld zone to protect the molten pool from atmospheric contamination. These transferred arc configurations connect the arc route physics to practical joining processes. Plasma cutting requires a strongly constricted arc to deliver very high heat flux to the workpiece. Figure 31 shows a typical plasma cutting torch design with axial or vortex injection of plasma-forming gas such as oxygen. Stick-type or button-type cathodes made of tungsten or hafnium are used in different torch implementations. Heat flux at the workpiece can be 100 to 200 kilowatts/cm2, at least an order of magnitude higher than arc welding. High constriction produces high current density and high core temperature even at relatively low currents such as 20 A. Newer directions include air-operated, air-cooled low-amperage torches for repair applications and high-current underwater cutting relevant to nuclear power plant dismantling. Plasma spraying is a major application of hot cathode torches. Spray material is typically a fine powder with mean particle diameter between 20 and 100 micrometers, carried by a gas stream into the plasma jet. Figure 32 shows the process. Powder particles accelerate, heat, and melt while traveling through the jet. When molten particles impact the substrate at 100 to 300 meters/s, the particles flatten into splats that build a coating. A broad range of materials can be sprayed when melting temperature and vaporization or decomposition temperature differ by at least 300 Kelvin. Plasma spraying is widely used for ceramics and can also be used for metals and alloys when oxidation control is acceptable. High-power plasma spray torches up to about 250 kilowatts have been developed, with particle feed rates up to 20 kilograms per hour for large components. A related low-pressure approach is PSPVD, using a high-power torch around 180 kilowatts to 3000 A with gas flow up to about 200 SLM. PSPVD can operate at pressures as low as 0.05 to 0.2 kilopascals, producing a very long plasma jet that can exceed 2 meters in length and reach about 0.4 meters in diameter. Coatings produced under such low-pressure conditions can show microstructures similar to EBPVD coatings. Figure 33 illustrates ceramic coating plasma sprayed on a large drum used for paper manufacturing applications. Figure 34 shows plasma-sprayed components in a typical jet engine, representing aerospace use cases for thermal barrier, wear-resistant, and abradable coatings. Cold-electrode plasma torches use water-cooled metal sleeves, often copper, steel, silver, or related alloys. These electrodes can operate with oxidizing or reducing plasma-forming gases. Cathode electron emission in cold-electrode torches is linked to evaporation and ionization of electrode material in small cathode spots, which implies material loss. Cathode spot diameters are reported around 1 to 2 millimeters for currents from 800 to 1400 A, with current densities around 10 to the power of 8 to 10 to the power of 9 amperes per square meter. Electrode erosion rate ER, expressed in micrograms per coulomb, is related to arc current I by EQ. 15. ER equals A, I to the power of M. The constants A and M depend on plasma gas and operating conditions, so erosion control becomes a primary design objective. A key erosion control strategy is to introduce strong vortex motion in the discharge cavity. Vortex flow drives the arc routes over electrode surfaces and spreads erosion over a larger area. Magnetic field coils can further enhance arc route rotation by applying a tangential electromagnetic force at the attachment point. Figure 35 shows a cold electrode torch concept developed by Aerospatiale with a field coil on the back electrode. Such designs can require high plasma gas flow rates, roughly 200 to 300 cubic meters per megawatt, which can yield relatively low jet enthalpy below about 10 kilowatt-hours per cubic meter. Typical power ratings are in the 1 to 3 megawatts range with arcade currents up to 1000 A and electrode voltages around 1.0 to 3 kilovolts. Figure 36 shows a cold electrode plasma torch concept developed by Westinghouse, including a family of torch models and operating ranges. Westinghouse torches commonly used air as the plasma gas and operated at power levels up to about 2 megawatts. Reported energy efficiency for these systems is in the 70% to 90% range, with specific enthalpy at the exit in the range H equals 8 to 19 megajoules per kilogram. Another scaling approach increases arc length using insulated segments and injection of cold gas between cathode and anode to renew the cold boundary layer around the arc column. This approach can raise arc voltage for the same current and push torch power toward the 6 megawatts range, while high gas flow such as 15,000 cubic meters per hour can keep enthalpy H0 relatively low. High-power cold electrode torches are valued for high-temperature operation under controlled conditions, high throughput and energy efficiency, compact systems, elimination of graphite electrodes, and reduced noise and process gas volumes. Cold electrode torches have supported large-scale melting and remelting applications in the metallurgical industry. Figure 37 shows a plasma shaft furnace used by General Motors for scrap remelting, heated by 6.2 megawatts plasma torches. Cold electrode torches are also used in transferred arc mode for tundish heating and other melting and remelting tasks. In this mode, the molten pool acts as an electrode and major energy input occurs at the arc route on the molten bath surface. Figure 38 shows a high-power plasma torch arrangement for ladle heating, where the goal is to hold molten steel temperature constant or slightly increasing. Extractive metallurgy applications face scale limits, because steel smelting rates near 30 T/H imply plasma furnace power near 100 megawatts, a level beyond present technology in practical multiple torch operation. Large-scale cold electrode plasma torches have been successful for treatment of hazardous waste materials. Thermal plasmas can decompose exposed materials, potentially into elemental constituents, which is useful for breaking down stable chemical compounds. A central technical challenge is quench control to prevent unwanted recombination products that can be carcinogenic or otherwise hazardous. High temperature enables fast and complete pyrolysis of organic wastes and melting or vitrification of inorganic waste, reducing volume and encapsulating non-destructible residues. High energy density supports smaller installations for comparable throughput, lowering capital cost and enabling small mobile units. Figure 39 illustrates a municipal solid waste destruction concept developed by Westinghouse, representative of plasma-based waste processing configurations. Thermal plasma waste processing can use different reaction modes depending on oxygen availability and desired products. Plasma pyrolysis refers to thermal breakdown without oxidation. Plasma gasification refers to incomplete oxidation of organic components to generate a combustible gas, often used in waste-to-energy approaches. Plasma compaction and vitrification combine gasification of organics with melting of inorganics and binding of hazardous metals in a ceramic matrix using appropriate fluxes. Candidate waste streams include municipal solid waste, hospital solid waste, incinerator bottom ash and fly ash, contaminated soil, sewage sludge, low-level radioactive waste, and difficult military wastes. Manufacturing wastes such as electric arc furnace dusts and aluminum dross can also be treated, and valuable materials can be recovered from waste streams, such as platinum from discarded exhaust catalysts. Segmented plasma torches were developed to replicate severe reentry flow conditions for materials testing. Reentry testing demands very high velocities, high temperatures, and controlled gas compositions, which thermal plasma technology can provide. Figure 40 shows a conceptual segmented plasma torch with multiple intermediate segments between cathode and anode. Each segment is water-cooled and electrically insulated from adjacent segments, and sheath gas is injected between segments to maintain a cold boundary layer around the arc channel. The design increases arc length and therefore voltage, providing a path to higher torch power. Figure 41 shows a wall-stabilized segmented high-power arc heater concept with power rating 60 megawatts, pressure 12 bar, current 5.4 kiloamperes, voltage 11 kilovolts, and airflow rate 1.4 kilograms per second. High-power arc heater facilities demonstrate how segmented torch concepts scale to reentry testing environments. Figure 42 shows a high-power aerospace wind tunnel at Arnold Engineering Development Center, associated with 30 to 70 megawatts operating range. Such sources can satisfy power requirements for testing, but runtime is typically short in minutes. Many commercial torches for other applications such as spraying, materials processing, metallurgy, or waste treatment are expected to operate for hundreds of hours, so duty cycle is a key differentiator. Segmented designs therefore occupy a specialized niche where short-duration extreme conditions matter most. The figure set Figure 40 to Figure 42 provides a coherent picture from torch concept to facility-scale implementation. Inductively coupled plasmas are electrodeless sources where energy is transferred into the discharge through electromagnetic coupling. This source family provides high-purity discharge environments with relatively large volume and low energy density compared with many arc devices. Operating atmospheres can be inert, oxidizing, or reducing, and pressure can range from soft vacuum up to a few atmospheres, roughly 10 kilopascals to 0.5 megapascals. Low-power operation around 5 to 10 kilowatts is widely used for trace element analysis using OES or MS. Figure 43 shows a typical OES plasma source using a quartz wall air-cooled open discharge. In this configuration, induction coil coupling sustains plasma without electrode contact in the discharge region. Inductively coupled plasmas are also used in fiber optics manufacturing for cladding of fiber optics preforms. Figure 44 shows a typical setup with a preform mounted horizontally on a coating lathe and an induction plasma directed toward the preform in an open discharge configuration. Silica grain is injected into the plasma plume, melts in flight, and deposits onto the preform surface. The process is typically run in batch mode with runtime of a few hours to deposit about 50 mm cladding thickness over a 1 meter long preform. Industrial success depends on reliable induction plasma sources suitable for continuous operation and repeatable thermal environments. These applications emphasize purity, controlled heating, and stable coupling over long processing intervals. Industrial induction plasma torches use robust confinement and cooling to handle high energy flux. Figure 45 shows a Techna induction plasma torch concept with a ceramic plasma confinement tube and high-velocity water film cooling. The The torch includes a gas distribution head, a polymer matrix composite body, and a water-cooled exit nozzle. A central axial injection path allows material feed at the center of the induction coil using a water-cooled injection probe. Probe tip position can be adjusted axially to tune processing conditions for different materials. Technotype induction torches have been scaled to power levels from about 15 kilowatts up to 350 kilowatts for synthesis and processing tasks. Induction plasma installations support coatings, material synthesis, and powder processing under controlled conditions. Reported application areas include deposition of protective coatings and near-net-shaped parts. Materials processing includes powder purification, densification, and spheroidization for both metallic and ceramic powders. Induction plasma can also support plasma melting and atomization of high-purity materials and synthesis of high-purity nanopowders. Figure 46 shows plasma deposition of refractory metal coatings on an X-ray target and a cylindrical graphite substrate. Figure 47 shows electron micrographs of molybdenum powder before and after treatment in an induction plasma, demonstrating improved particle sphericity and density. Quantitative powder improvements can be evaluated by density and flowability metrics. After induction plasma treatment, molybdenum powder tap density increases from 2.3 to 6.6 grams per cubic centimeter. Improved flowability is reported using a Hull flow value of 13.0 seconds/50 G for plasma-treated powder. The untreated powder is described as non-flowable under the same flow test framing. These results connect the visual evidence in Figure 47 to measurable handling and packing performance. The combined figure set Figure 46 and Figure 47 links plasma deposition capability to powder morphology control in induction plasma processing.